Songkhla University or PSU is the first and largest university in southern Thailand. Today, PSU is a leading research-based university in Asia, committed to academic excellence, reputable research, and innovation. That's why PSU always ranked in the top 10 university of Thailand. The Faculty of Science was established in 1967, the year the university was founded. The Faculty of Science is considered to be one of the largest and the most outstanding faculties in the university. Over 50 years ago, the Faculty of Science has sought to provide quality higher education, conduct research to the benefit of science and local industry, to provide services and contribute actively and responsibly to the population in the surrounding communities and provinces in southern Thailand. The Faculty of Science opens programs for all degrees programs, including bachelor's, master's, and doctoral degrees. The faculty now offers 12 undergraduate and 30 graduate programs. In addition, the faculty also provides short courses for international students. For graduate programs, the faculty can accommodate international students. All the programs are divided into 4 divisions: physical science, biological science, computational science, and health and applied sciences. Here are the details about the programs for each division. Basically, there are 2 semesters each academic year. Each semester is approximately 18 weeks long. Therefore, the first semester runs from the first week of June to the first week of October. Then, the second semester runs from the last week of October to the last week of February. The tuition fee for bachelor's degree is 27,000 Thai baht, or approximately $900 per semester, while the tuition fee for both master's and doctoral degrees are 56,000 Thai baht, or approximately $1,900 per semester. The faculty also provide you some scholarships. For more information on scholarships, please contact us. The Faculty of Science is proud of its distinguished record of achievement in teaching, research, development, and services to the community. It has contributed significantly to the development of the country and consistently turned out well-qualified graduates of high professional standing. There are 11 main research fields and 15 research networks. At the Faculty of Science, you can enjoy excellent teaching and learning facilities. The faculty has its own specialized laboratories with adequate modern equipment, and it opens to all staff and students. Therefore, the faculty is able to bring science to the real world. You can conduct all experiments through the laboratory by yourself, and you will get a valuable experience that you may have never seen before. Currently, the Faculty of Science gives priority to the development of internationalization in the institution. Therefore, our faculty, staff, and students have the opportunity to gain overseas experiences, as well as enhance their international and cross-cultural learning at home and abroad. As the faculty places great importance on all international students, the faculty increases and diversifies the international undergraduate students and has a comprehensive and strategic international graduate student recruitment plan. In terms of the academic aspect, the faculty support research international priorities in order to enhance their reputation on the world stage. These are the result of more than 40 collaborative institutions around the world. Now, let's see the attitude of our international students toward the Faculty of Science. Why did they choose to study here? For more information, please contact us.
นับแต่อรุณรุ่งแห่งอารยธรรมจวบจนวันนี้มนุษยชาติรุ่นแล้วรุ่นเล่าเฝ้ามองท้องฟ้าตามหาความรู้จากเอกภพส่งต่อกันมาตลอดสายทานแห่งการเวลาเพื่อตอบคำถามพื้นฐานที่สุดและสำคัญที่สุดทั้งหลาย
วิทยาศาสตร์นี่จริงๆก็คือเป็นเรื่องของความรู้ที่เกี่ยวกับธรรมชาติในส่วนที่เรียกว่าดาราศาสตร์นี่คือความรู้ของเราที่เกี่ยวกับเอกภพเราจำเป็นอย่างยิ่งที่จะต้องศึกษาในสิ่งที่มันมากกว่าโลกนะครับทุกคนก็ตั้งคำถามอยู่เสมอตั้งแต่อดีตว่าเราอยู่โดดเดี่ยวบนโลกใบนี้จริงหรือเปล่าและมันยังมีชีวิตที่มีเทคโนโลยีอย่างที่เรามีอยู่ในปัจจุบันนี้อยู่ที่อื่นอีกไหมนะครับเพราะฉะนั้นดาราศาสตร์จะเป็นการศึกษาที่ให้คำตอบที่ยิ่งใหญ่เหล่านี้ได้นะครับ
ดาราศาสตร์นั้นเป็นโจทย์ยากท้าทายพลังความคิดและจินตนาการของเราแต่โจทย์ยากจะสร้างคนเก่งซึ่งเป็นทรัพยากรอันมีค่านำพาประเทศไทยสู่อนาคต
สิ่งที่สำคัญที่สุดคือต้องพัฒนาคนเพราะฉะนั้นการที่เราสร้างบุคลากรโดยอาศัยวิทยาศาสตร์ขั้นสูงเนี่ยก็จริงๆก็เป็นแนวทางเดียวกับที่ประเทศอื่นๆใช้ได้ผลนะครับ
สถาบันวิจัยดาราศาสตร์แห่งชาติองค์การมหาชนก่อตั้งขึ้นเมื่อพุทธศักราช 2552 ตลอดทศวรรษแรกที่ผ่านไปดาราศาสตร์ไทยเติบโตก้าวกระโดดในหลายมิติทั้งโครงสร้างพื้นฐานบุคลากรงานวิจัยและการเผยแพร่ดาราศาสตร์สู่ประชาชน
สถาบันวิจัยดาราศาสตร์แห่งชาติองค์การมหาชนจะทำให้ดาราศาสตร์ของประเทศเนี่ยมีความเจริญก้าวหน้าทั้งทางด้านของการพัฒนากำลังคนการพัฒนาโครงสร้างพื้นฐานและการพัฒนาทางด้านวิชาการต่อไป
อีกแรงหนุนเนื่องอันสำคัญยิ่งของดาราศาสตร์ไทยคือพระมหากรุณาธิคุณในสมเด็จพระกนิษฐาธิราชเจ้ากรมสมเด็จพระเทพรัตนราชสุดาสยามบรมราชกุมารีเจ้าฟ้านักดาราศาสตร์ผู้ทรงใฝ่พระราชหฤทัยในดาราศาสตร์ตั้งแต่ยังทรงพระเยาว์ตราบจนปัจจุบัน
ตามที่ได้มีโอกาสถวายงานสมเด็จพระกนิษฐาธิราชเจ้ากรมสมเด็จพระเทพรัตนราชสุดาในช่วง30 กว่าปีที่ผ่านมาเนี่ยทรงทำให้เห็นถึงความสำคัญของดาราศาสตร์ที่เป็นวิทยาศาสตร์พื้นฐานเนี่ยต่อการพัฒนาวิทยาศาสตร์เทคโนโลยีของประเทศเราแล้วก็ในเรื่องของความร่วมมือระหว่างประเทศทำให้เกิดโครงการขนาดใหญ่ในการพัฒนาทางด้านดาราศาสตร์ของประเทศไทยของเราทั้งในปัจจุบันแล้วก็ที่เราจะมีต่อไปในอนาคตด้วย
สถาบันวิจัยดาราศาสตร์แห่งชาติองค์การมหาชนมุ่งขับเคลื่อนดาราศาสตร์ไทยให้ก้าวหน้าเริ่มจากโครงสร้างพื้นฐานดาราศาสตร์ณหอดูดาวแห่งชาติที่จะเป็นแหล่งรวบรวมเรียนรู้และวิจัยองค์ความรู้ดาราศาสตร์เพื่อประโยชน์มหาชนเครือข่ายหอดูดาวสำหรับประชาชน5 แห่งทั่วประเทศปัจจุบันเปิดบริการแล้ว3 แห่งได้แก่หอดูดาวเฉลิมพระเกียรติ7 รอบพระชนมพรรษานครราชสีมาฉะเชิงเทราสงขลาและโครงการในอนาคตได้แก่ขอนแก่นและพิษณุโลกอุทยานดาราศาสตร์สิรินธรคือศูนย์กลางพัฒนาดาราศาสตร์ไทยทางด้านงานวิจัยพัฒนาและเสริมศักยภาพบุคลากรมีห้องปฏิบัติการขั้นสูงอันเป็นแหล่งฟูมฟักความรู้ใหม่ๆสร้างงานวิจัยมาตรฐานโลกได้รับเลือกให้เป็นศูนย์ฝึกอบรมดาราศาสตร์นานาชาติภายใต้ยูเนสโกแห่งแรกของโลกและล่าสุดหอสังเกตการดาราศาสตร์วิทยุแห่งชาติเสริมทัพดาราศาสตร์ไทยและประกาศศักดิ์ศรีเชียงใหม่ในฐานะนครหลวงแห่งดาราศาสตร์อาเซียนทั้งยังมีโครงข่ายกล้องโทรทัศน์ทั่วโลกได้แก่จีนชิลีอเมริกาและออสเตรเลียสนับสนุนงานวิจัยไทยและนานาประเทศสถาบันวิจัยดาราศาสตร์แห่งชาติองค์การมหาชนยังทำหน้าที่เผยแพร่ดาราศาสตร์สู่ประชาชนผ่านกิจกรรมสังเกตการณ์งานเสวนาและการอบรมต่างๆสร้างแรงบันดาลใจแก่ครูนักเรียนเยาวชนนักดาราศาสตร์สมัครเล่นและประชาชนทั่วไป
เราคาดหวังก็คือเรื่องของการพัฒนาเทคโนโลยีด้วยองค์กรเองทำให้ บุคลากรของสถาบันไม่ว่าจะเป็นวิศวกรเป็นช่างเทคนิคเนี่ยได้มีโอกาสในการพัฒนาศักยภาพของตัวเองแล้วก็สร้างสรรค์นวัตกรรมที่เป็นเทคโนโลยีใหม่ๆออกมาน
อกจากจะสร้างโครงสร้างพื้นฐานและยังหมายรวมถึงการพัฒนาบุคลากรอีกด้วยอุปกรณ์ที่พัฒนาขึ้นก็อาจต่อยอดไปสู่วงการอื่นๆได้ต่อไปทั้งหมดนี้คือความมุ่งมั่นของเราที่จะสร้างอนาคตประเทศไทยด้วยความรู้และเทคโนโลยีจากดาราศาสตร์สร้างแรงบันดาลใจให้คนไทยมีใจรักวิทยาศาสตร์และจับมือวงการดาราศาสตร์ทั่วโลกพัฒนาความรู้ของมนุษยชาติร่วมกันต่อยอดภูมิปัญญาที่สั่งสมมานับพันปีเพื่อวันข้างหน้าของเราทุกคน
เมื่อโลกก้าวเข้าสู่ศตวรรษที่ 21 วิทยาศาสตร์เทคโนโลยีและนวัตกรรมจึงกลายมาเป็นส่วนหนึ่งในชีวิตประจำวันของเราทุกคนอย่างหลีกเลี่ยงไม่ได้ทุกสิ่งที่อยู่รอบตัวเราล้วนแต่เกิดขึ้นจากองค์ความรู้ซึ่งถูกคิดค้นและวิวัฒนาการเป็นเทคโนโลยีที่นำไปต่อยอดเป็นนวัตกรรมเพื่อตอบสนองความต้องการของเราอย่างไม่มีที่สิ้นสุดสำหรับประเทศไทยการพัฒนาวิทยาศาสตร์เทคโนโลยีและนวัตกรรมนับว่าเป็นบทบาทสำคัญบทบาทหนึ่งของกระทรวงวิทยาศาสตร์และเทคโนโลยีที่จะผลักดันให้เกิดการนำไปใช้ประโยชน์ในการพัฒนาประเทศและคุณภาพชีวิตของผู้คนอย่างยั่งยืนกระทรวงวิทยาศาสตร์และเทคโนโลยีจึงได้จัดตั้งสถาบันวิจัยแสงซินโครตรอนขึ้นโดยมีเป้าหมายให้สถาบันแห่งนี้เป็นดั่งห้องปฏิบัติการกลางของประเทศที่มีความพร้อมในด้านเครื่องมืออุปกรณ์วิทยาศาสตร์ที่ทันสมัยอีกทั้งยังส่งเสริมให้เกิดการสร้างองค์ความรู้ทางวิทยาศาสตร์ในกลุ่มนักวิจัยทั้งภาครัฐและภาคเอกชนอย่างเต็มที่ส่งผลให้เกิดเทคโนโลยีที่นำไปสู่การสร้างนวัตกรรมเพื่อยกระดับคุณภาพชีวิตของคนไทยและเครื่องมืออันเป็นหัวใจสำคัญของงานวิจัยที่ทางสถาบันทุ่มเทมาตลอดนั่นก็คือเครื่องกำเนิดแสงที่มีความเข้มแสงสูงซึ่งให้ความสว่างกว่าแสงในเวลากลางวันกว่าล้านเท่านักวิจัยจึงสามารถนำแสงไปใช้ประโยชน์ทางด้านการศึกษาค้นคว้าหรือการวิจัยและพัฒนาได้อย่างเต็มประสิทธิภาพไม่ว่าจะเป็นการนำไปใช้ศึกษาโครงสร้างในระดับอะตอมที่ประกอบขึ้นเป็นวัสดุชนิดต่างๆทำให้เราสามารถเข้าใจคุณสมบัติทางกายภาพของวัสดุเช่นความแข็งความยืดหยุ่นการนำไฟฟ้ารวมไปถึงการปรับปรุงคุณภาพของวัสดุต่างๆได้ตามความต้องการเครื่องกำเนิดแสงที่กล่าวถึงนี้ถูกเรียกว่าเครื่องกำเนิดแสงซินโครตรอนซึ่งสามารถผลิตแสงที่มีคุณสมบัติอันโดดเด่นกว่าเครื่องกำเนิดแสงประเภทอื่นๆเช่นความเข้มแสงอันมหาศาลและยังครอบคลุมช่วงความยาวคลื่นตั้งแต่รังสีอินฟราเรดอัลตราไวโอเลตไปจนถึงรังสี Xซึ่งเป็นคุณสมบัติพิเศษที่ทำให้สามารถส่องดูโครงสร้างทางกายภาพในทุกระดับตั้งแต่การศึกษาพันธะในสารชีวโมเลกุลของเซลล์สิ่งมีชีวิตด้วยแสงอินฟราเรดการตรวจสอบสถานะทางเคมีของธาตุที่เจือปนผิวโลหะด้วยแสงอัลตราไวโอเลตไปจนถึงการศึกษาโครงสร้างผลึกโปรตีนด้วยรังสี X คุณสมบัติพิเศษทั้งหมดของแสงซินโครตรอนที่กล่าวมานี้จึงเป็นตัวช่วยสำคัญที่ช่วยให้เรารู้จักและเข้าใจธรรมชาติพฤติกรรมของสสารได้มากยิ่งขึ้นอีกทั้งยังสามารถนำไปใช้แก้ไขปัญหาในด้านการผลิตรวมทั้งพัฒนาผลิตภัณฑ์ใหม่ในภาคอุตสาหกรรมได้อย่างเต็มประสิทธิภาพเครื่องกำเนิดแสงซินโครตรอนจะผลิตแสงซินโครตรอนจากอนุภาคที่เรียกว่าอิเล็กตรอนซึ่งปลดปล่อยออกมาจากผิวโลหะที่ถูกป้อนด้วยกระแสไฟฟ้าจนเกิดความร้อนจากนั้นอนุภาคอิเล็กตรอนจำนวนมหาศาลจะถูกส่งเข้าสู่เครื่องเร่งอนุภาคเพื่อทำการเร่งความเร็วของอิเล็กตรอนให้มีความเร็วใกล้เคียงความเร็วแสงหรือความเร็วประมาณ 300,000 กิโลเมตรต่อวินาทีจากนั้นอิเล็กตรอนจะถูกส่งต่อเข้าสู่วงกักเก็บอิเล็กตรอนซึ่งเป็นบริเวณที่จะผลิตแสงซินโครตรอนอิเล็กตรอนที่อยู่ในท่อสุญญากาศจะถูกบังคับให้เลี้ยวเบนกระทันหันทำให้อิเล็กตรอนเกิดการสูญเสียพลังงานและปลดปล่อยพลังงานออกมาในรูปของแสงซินโครตรอนนั่นเองแสงซินโครตรอนที่ผลิตขึ้นมานั้น จะต้องมีระบบลำเลียงเพื่อนำแสงไปใช้ประโยชน์ในด้านต่างๆนักวิทยาศาสตร์จึงได้คิดค้นและสร้างระบบลำเลียงแสงเพื่อนำแสงซินโครตรอนไปส่งยังบริเวณที่นักวิทยาศาสตร์ทำการทดลองหรือ End Station ต่อไปเครื่องกำเนิดแสงซินโครตรอนที่ติดตั้งอยู่ที่สถาบันวิจัยแสงซินโครตรอนนั้นเป็นหนึ่งในเครื่องกำเนิดแสงซินโครตรอนที่มีอยู่ประมาณ50เครื่องจาก 20 ประเทศชั้นนำทางด้านวิทยาศาสตร์และเทคโนโลยีทั่วโลกเครื่องกำเนิดแสงซินโครตรอนซึ่งตั้งอยู่ที่สถาบันวิจัยแสงซินโครตรอนของไทยมีขนาดพลังงาน 1,200 ล้านอิเล็กตรอนโวลต์มีเส้นรอบวงของวงกักเก็บอิเล็กตรอนขนาด 81.3 เมตรซึ่งเป็นระบบลำเลียงแสงที่พร้อมให้บริการนักวิจัยในการใช้ประโยชน์ด้านการศึกษาค้นคว้าทั้งหมด12ระบบลำเลียงแสงครอบคลุมการใช้งานเกือบทุกสาขาวิชาตั้งแต่การเกษตรสิ่งแวดล้อมอาหารยาเครื่องสำอางวัสดุศาสตร์อุตสาหกรรมประเภทต่างๆเช่นยางโพลิเมอร์โลหะปูนวัสดุก่อสร้างและในด้านอื่นๆอีกมากมายนอกจากแสงซินโครตรอนแล้วทางสถาบันยังมีการพัฒนาเทคโนโลยีที่เกี่ยวข้องกับแสงซินโครตรอนอีกหลายด้านเช่นเทคโนโลยีสุญญากาศเทคโนโลยีควบคุมความแม่นยำสูงเทคโนโลยีคลื่นความถี่วิทยุและเทคโนโลยีการผลิตโครงสร้างขนาดไมโครเมตรซึ่งเทคโนโลยีเหล่านี้จะเป็นประโยชน์อย่างมากมายมหาศาลในอุตสาหกรรมต่างๆของประเทศกว่า10ปีที่ทางสถาบันวิจัยแสงซินโครตรอนได้เปิดให้บริการมานั้นเราได้ก้าวไปข้างหน้าเคียงข้างนักวิจัยของประเทศผ่านผลงานที่เด่นชัดจากจำนวนผลงานวิจัยกว่า600ผลงานอีกทั้งทางสถาบันยังได้ช่วยสนับสนุนให้อุตสาหกรรมของไทยสามารถสร้างมูลค่าเพิ่มทางเศรษฐกิจเป็นเม็ดเงินหลายพันล้านบาทตลอดเวลา5ปีที่ผ่านมาทางสถาบันจึงมีความมั่นใจในประสบการณ์และความชำนาญที่สั่งสมมาอย่างต่อเนื่องด้วยศักยภาพของบุคลากรที่เป็นกำลังสำคัญของสถาบันและของประเทศอีกทั้งเรายังมีความพร้อมที่จะช่วยให้คนไทยและอุตสาหกรรมไทยมีการพัฒนาอย่างต่อเนื่องและยั่งยืนเพื่อยกระดับคุณภาพชีวิตความเป็นอยู่ของคนไทยให้ดีขึ้นและเพื่อให้วิทยาศาสตร์เทคโนโลยีและนวัตกรรมกลายเป็นส่วนหนึ่งของคนไทยในศตวรรษที่ 21 นี้
สถาบันส่งเสริมการสอนวิทยาศาสตร์และเทคโนโลยี สสวท กระทรวงศึกษาธิการเป็นองค์กรหลักของประเทศทำหน้าที่ชี้ทิศทางประสานส่งเสริมและเพิ่มประสิทธิภาพการเรียนการสอนวิทยาศาสตร์คณิตศาสตร์และเทคโนโลยีทั้งในและนอกสถานศึกษาให้นักเรียนพัฒนาศักยภาพขึ้นเป็นประชากรที่มีความรู้นักวิชาชีพฐานดีและนักวิทยาศาสตร์ชั้นนำในอนาคตผลงานเด่นตามภารกิจสำคัญของสสวท ประกอบด้วยการยกระดับคุณภาพการศึกษาสสวท ได้พัฒนาสื่อและกระบวนการจัดการเรียนรู้วิทยาศาสตร์คณิตศาสตร์และเทคโนโลยีที่มีคุณภาพตามมาตรฐานสากลเน้นการคิดวิเคราะห์แก้ปัญหาและการนำไปใช้ตามหลักสูตรแกนกลางการศึกษาขั้นพื้นฐานพุทธศักราช 2551 ฉบับปรับปรุงพุทธศักราช 2560 พร้อมใช้ครบทั้ง 12 ชั้นปีพัฒนาครูและบุคลากรทางการศึกษาผ่านหลักสูตรออนไลน์การจัดการเรียนรู้วิทยาการคำนวณ Coding for Teacher หรือ C4T อบรมครูพี่เลี้ยงและครูผู้สอนวิทยาศาสตร์คณิตศาสตร์และเทคโนโลยีให้มีความรู้ความเข้าใจและสามารถจัดประสบการณ์การเรียนรู้ได้และร่วมกับมหาวิทยาลัยราชภัฏ 38 แห่งอบรมอาจารย์จากมหาวิทยาลัยราชภัฏศึกษานิเทศและครูแกนนำในพื้นที่เพื่อสร้างวิทยากรท้องถิ่นและอบรมครูประจำการให้มีสมรรถนะของครูยุคใหม่สำหรับการเรียนรู้ในศตวรรษที่ 21 ตามแนวสมรรถนะของพิซซ่าการสร้างความเสมอภาคทางการศึกษาสสวท นำร่องพัฒนาโรงเรียนคุณภาพวิทยาศาสตร์คณิตศาสตร์และเทคโนโลยีตามมาตรฐานสสวท ใน 3 จังหวัดประกอบด้วยจังหวัดประจวบคีรีขันธ์จังหวัดพระนครศรีอยุธยาจังหวัดหนองคายและ2 โรงเรียนในกรุงเทพมหานคร คือโรงเรียนดาราคามและโรงเรียนปทุมคงคาและพัฒนาครูผู้สอนวิชาวิทยาศาสตร์คณิตศาสตร์และเทคโนโลยีในโรงเรียนนำร่องอบรมครูผู้สอนวิชาวิทยาศาสตร์คณิตศาสตร์ในโรงเรียนโครงการสมเด็จพระกนิษฐาธิราชเจ้ากรมสมเด็จพระเทพรัตนราชสุดาสยามบรมราชกุมารีประกอบด้วยครูแกนนำครูปฐมวัยครูผู้สอนระดับประถมศึกษาและมัธยมศึกษาจากโรงเรียนตำรวจตระเวนชายแดนและครูผู้สอนจากโรงเรียนวังไกลกังวลในพระบรมราชูปถัมภ์การมุ่งความเป็นเลิศและสร้างขีดความสามารถในการแข่งขันของประเทศสสวท.ดำเนินการคัดเลือกผู้มีความสามารถพิเศษด้านวิทยาศาสตร์และเทคโนโลยีเข้ารับทุนพัฒนาและส่งเสริมผู้มีความสามารถพิเศษทางวิทยาศาสตร์และเทคโนโลยีหรือทุนพสวท.คัดเลือกนักเรียนระดับชั้นประถมศึกษาปีที่ 3 และชั้นประถมศึกษาปีที่ 6 เข้าโครงการพัฒนาอัจฉริยภาพทางวิทยาศาสตร์และคณิตศาสตร์เพื่อส่งเสริมทักษะกระบวนการทางวิทยาศาสตร์และคณิตศาสตร์จัดส่งผู้แทนประเทศไทยไปแข่งขันคณิตศาสตร์วิทยาศาสตร์โอลิมปิกระหว่างประเทศวิชาคณิตศาสตร์คอมพิวเตอร์เคมีชีววิทยาและฟิสิกส์การขับเคลื่อนการศึกษาด้วยเทคโนโลยีและนวัตกรรมสู่การศึกษาแบบ New Normal สสวท.ได้ปรับรูปแบบการเรียนรู้เพื่อรองรับสถานการณ์การแพร่ระบาดของโรคติดเชื้อไวรัสโคโรนาหรือโควิด -19 จากเฉพาะการเรียนรู้ในห้องเรียนให้เป็นการเรียนรู้ได้ทุกที่ทุกเวลาเลือกเนื้อหาได้ตามความต้องการด้วยการพัฒนาบทเรียนออนไลน์ภายใต้โครงการสอนออนไลน์โปรเจกต์ 14สสวท.ยกระดับการเรียนรู้วิทยาศาสตร์คณิตศาสตร์และเทคโนโลยีสร้างเด็กฉลาดรู้ครูคุณภาพสูงแข่งขันได้ด้วยฐานสมรรถนะ
Physics is the key to science and technology. TIP Center, the Thailand Center of Excellence in Physics, is devoted to improving the level of physics education and research in Thailand. This will improve science technology in an innovation-based society. The mission of the TIP Center is to provide scientific tools and knowledge to serve societal needs, as well as to develop practical applications of physics innovations and technology. Success in physics will help advance science and technology, advance private industry, and lead to increasing economic self-reliance and improvement in the quality of life of Thai people. TIP Center philosophy is based on the wisdom of His Majesty the late King Bhumibol Adulyadej, expressed to the USA Congress in 1960. There is one concept that needs to be emphasized. American assistance is to enable the Thais to achieve their objectives through their own efforts. I need hardly say that this concept has our complete endorsement. Indeed, there is a precept of the Lord Buddha which says, "Thou art thine own refuge." We are grateful for American aid, but we intend one day to do without it. TIP Center will improve Thai society through research activities in 4 directions: physics education, fundamental physics, applied physics,
Sawadika. Good morning, ladies and gentlemen. Good morning from Hat Yai, Songkhla, Thailand. On behalf of the organizing committees, I would like to welcome all of you to the Siam Physics Congress 2021 or SPC 2021. Some of you might watch this from the SPC website, and some of you might watch this from the Facebook Live. on the Faculty of Science, Prince of Songkhla University Facebook page. Today we are very excited to have a special keynote speaker, Professor Takaaki Kajita, a 2015 Nobel Laureate in Physics. I just would like to inform you that during the plenary talk, if you would like to ask some questions, you may type your question on the Facebook Live, and we will deliver your questions to the speaker. The conference abstract book is now available on our main conference website, so you can check if you would like to see the abstract book. So now we shall start with the formal opening ceremony. Associate Professor Bunraksa Sunthorntham, President of Thai Physics Society. Associate Professor Dr. Anchana Prathep, Dean of Faculty of Science, Prince of Songkhla University. Distinguished speakers and participants, ladies and gentlemen, on behalf of Thai Physics Society, Faculty of Science, Prince of Songkhla University, and the organizing committees, I would like to welcome you to the Siam Physics Congress 2021. First of all, I would like to introduce myself. My name is Dr. Surirat Chana, the member of the organizing committees, Faculty of Science, Prince of Songkhla University, and I will be the MC for today. This SPC 2021 will be held for 2 days, from 24th to the 25th of May 2021 via Zoom meeting. We hope everyone will stay with us and enjoy the online conference. In this morning, we will have the opening ceremony from 9 to 9:30 a.m., followed by the plenary talk by the 2015 Nobel Laureate in Physics at 9:30 a.m. until 10:30 a.m. And after that, we will have oral sessions, including several invited speakers for the entire day, tomorrow, and also today. Before we begin our opening ceremony, I would like to thank our generous sponsors as follows. The Council of Scientific and Technological Association of Thailand, National Astronomical Research Institute of Thailand, Synchrotron Light Research Institute Public Organization, the Institute for the Promotion of Teaching Science and Technology, Thailand Center of Excellence in Physics, National Research Council of Thailand, Rights Instruments Corporation Limited, Thailand Institute of Nuclear Technology, Society of Exploration Geophysicists, Nuclear Society of Thailand, and CPO Public Company Limited. Now we are honored to welcome the President of Prince of Songkhla University, Assistant Professor Dr. Niwat Kaew-Pradap, to give the welcome speech, and followed by Associate Professor Dr. Anchana Prathep, Dean of Faculty of Science, to give the conference report. Please welcome.
The President of Thai Physics Society, Dean of the Faculty of Science, Prince of Songkhla University, distinguished guest speakers, delegates, and participants. On behalf of Prince of Songkhla University, it is my pleasure and honor to welcome all distinguished participants involved in the field of physics from all over the world to the 16th Siam Physics Congress, or SPC 2021 today. First of all, may I thank Associate Professor Bunraksa Sunthorntham, the President of Thai Physics Society, for graciously presiding the opening of this international conference today. Prince of Songkhla University is honored and pleased to serve as co-host of the SPC 2021. A big thanks also go to our partnering organizer, the Thai Physics Society. The SPC 2021 features presentations in 21 different topics, ranging from cutting-edge fundamental physics research to innovative works ready to make impacts in society. This year, we received over 200 submissions from around the world, making this conference truly international. Therefore, connected from Japan today, we gladly welcome the 2015 Nobel Laureate in Physics, Professor Takaaki Kajita, for a talk on neutrinos. At this occasion, I would like to express my honored appreciation to the organizing team, sponsors, distinguished speakers, students, and my academic fellows for making the SPC 2021 possible. Finally, I thank everyone here who joins and shares wonderful ideas and experience with the audience. I am certain that the Siam Physics Congress 2021 provides an encouraging atmosphere for the researchers and students to thrive, performing high-quality research based on the idea. Change brings improvement, and to further expand their expertise on international level and inspire innovation that will benefit mankind. According to the COVID-19 pandemic, we only met online. But once the situation allows you to visit Thailand, we as PSU are delighted to welcome you all. Thank you very much.
President of Thai Physics Society, Professor บุญรักษาสุนทรธรรม President of Prince of Songkhla University, Professor นิวัฒน์แก้วประดับ Distinguished delegates and participants. Welcome to PSU. In 2020, the Siam Physics Congress was successfully conducted with the mutual interest agreement between the Physics Society and Mahidol University. This year, the Thai Physics Society and Prince of Songkhla University are organizing the SPC 2021. The conference aims to provide a general forum for enhancing interdisciplinary interaction, dialogue, and collaboration among students, researchers, faculty members, and government representatives, as well as practitioners from university and industry. This conference provides developmental networking opportunities with the aim to integrate and apply physics in teaching and, of course, developing our country. We thankfully appreciate the effort of our plenary speaker, the 2015 Nobel Laureate in Physics, Professor Takaaki Kajita, from Institute of Cosmic Ray Research, the University of Tokyo, Japan, with his expertise in neutrinos and gravitational waves. There are more than 20 invited speakers from around the world join us, sharing their expertise. Thank you all for being here. Today, we have more than 270 participants and more than 180 presentations, a total of over 21 topics covering the full spectrum of physics while connecting scientists from Australia, Japan, Taiwan, and Thailand. Despite the COVID-19 restrictions that everyone facing now, we are successful arranged the SPC 2021. May this bring us together here, and on the bright side, this actually give us a great opportunity to really broadcast the opening ceremony as well as the plenary talk on a special session on the future of Thailand, Tokamak TT1 live on the official social media channel, and therefore spreading the vision of SPC out to the world. We combine various areas of physics and its applications to excel and make contribution to the sustainable development of nations through science, technology, and innovation. On behalf of the Faculty of Science, I am very much appreciate all the sponsors and everyone contribute to this conference. Finally, as the representative organizer of 16th Siam Physics Congress, I hope that the event will allow us jointly share our expertise in the area of mutual interest as well as lead us not only to long-lasting relations but also to keep abreast of the needs of our region worldwide. Thank you everyone. Thank you.
Thank you very much, Professor Niwat Kaeopadap and Professor Anchana Pratep for the welcome speech and the conference report. Next, please welcome Associate Professor Bunraksa Sunthorntham, the President of Thai Physics Society, to give the opening speech for SPC 2021. Please welcome.
Okay. Thank you. Good morning, President of Prince of Songkla University, Dean of the Faculty of Science, Professor Takaaki Kajita, our keynote speaker at the plenary session today, Organizing Committee of Prince of Songkla University, honorary guests, participants, ladies and gentlemen. On behalf of the Thai Physics Society, I am delighted to have the opportunity to chair the opening session of the 16th SPC 2021 today. This year, we have accepted about 184 registrations from participants to join our full online meeting. There are 25 invited speakers, 82 oral presentations, and 77 poster presentations in 21 specialized fields of physics. I would like to express my sincere thanks to our co-host institute, Prince of Songkla University, for their hard work and well preparation to neaten the SPC 2021. The advancement in physics, both pure and applied physics, for the 21st century has enhanced the role of physics in advancing the new knowledge, the new discoveries, and the new application and innovation to various business sector and industry. Physicists have made the first detection of neutrinos that can be traced to carbon, nitrogen, oxygen fusion inside the sun, or as we know, well as the CNO cycle. There are several sites of neutrino detectors in the world that contribute such an important discovery in physics. And one of the important sites of neutrino experiment using the Kamiokande detector and its successor, the Super Kamiokande, at the Institute of Cosmic Radiation Research in Japan. This year at the SPC 2021, it is our great honor and pride to have Professor Takaaki Kajita, who was awarded a Nobel Prize in Physics in 2015 on the neutrino experiment, as our keynote speaker today. On behalf of the organizing committee, we feel deeply appreciate to Professor Takaaki Kajita for your kind acceptance to our invitation. And last but not least, I would like to thank all our cooperative institutes and sponsors for making the SPC 2021 possible today. And your continued support would be a stronghold in strengthening and keeping sustainability of our physics community in the future. Now it's time for me to declare the Siam Physics Congress 2021 open. Thank you very much.
Thank you very much, Associate Professor Bullaksa Sunthorntham, for the opening speech. Now the Siam Physics Congress 2021 is officially opened. But at this time, we still have a little time before the plenary talk, as the talk will start at 9:30 a.m. So let me tell you briefly about us, the organizing committee. This year, the SPC is hosted by the Faculty of Science, Prince of Songkhla University. Unfortunately, because of the coronavirus outbreaks all over the world, this SPC is fully online. And this is the first time that we host fully online conference. I myself is the first time being an MC for the online conference too. So we truly apologize for any mistakes that might happen during the conference and hope that next year we will see you again in person. We agree that the communication face-to-face is definitely better. However, the research cannot stop. So that's why we are here. So before we move to the keynote talk, I would like to show you a short video presentation about Faculty of Science, Prince of Songkhla University. Please enjoy your video.
Prince of Songkhla University, or PSU, is the first and largest university in southern Thailand. Today, PSU is a leading research-based university in Asia, committed to academic excellence, reputable research, and innovation. That's why PSU always ranks in the top 10 university of Thailand. The Faculty of Science was established in 1967, the year the university was founded. The Faculty of Science is considered to be one of the largest and the most outstanding faculties in the university. Over 50 years ago, the Faculty of Science has sought to provide quality higher education, conduct research to the benefit of science and local industry, to provide services and contribute actively and responsibly to the population in the surrounding communities and provinces in southern Thailand. The Faculty of Science opens programs for all degrees programs, including bachelor's, master's, and doctoral degrees. The faculty now offers 12 undergraduate and 30 graduate programs. In addition, the faculty also provides short courses for international students. For graduate programs, the faculty can accommodate international students. All the programs are divided into 4 divisions: physical science, biological science, computational science, and health and applied sciences. Here are the details about the programs for each division. Basically, there are 2 semesters each academic year. Each semester is approximately 18 weeks long. Therefore, the first semester runs from the first week of June to the first week of October. Then, the second semester runs from the last week of October to the last week of February. The tuition fee for bachelor's degree is 27,000 Thai baht, or approximately $900 per semester, while the tuition fee for both master's and doctoral degrees are 56,000 Thai baht, or approximately $1,900 per semester. The faculty also provide you some scholarships. For more information on scholarships, please contact us. The Faculty of Science is proud of its distinguished record of achievement in teaching, research, development, and services to the community. It has contributed significantly to the development of the country and consistently turned out well-qualified graduates of high professional standing. There are 11 main research fields and 15 research networks. At the Faculty of Science, you can enjoy excellent teaching and learning facilities. The faculty has its own specialized laboratories with adequate modern equipment, and it opens to all staff and students. Therefore, the faculty is able to bring science to the real world. You can conduct all experiments through the laboratory by yourself, and you will get a valuable experience that you may have never seen before. Currently, the Faculty of Science gives priority to the development of internationalization in the institution. Therefore, our faculty, staff, and students have the opportunity to gain overseas experiences, as well as enhance their international and cross-cultural learning at home and abroad. As the faculty places great importance on all international students, the faculty increases and diversifies the international undergraduate students and has a comprehensive and strategic international graduate student recruitment plan. In terms of the academic aspect, the faculty support research international priorities in order to enhance their reputation on the world stage. These are the result of more than 40 collaborative institutions around the world. Now, let's see the attitude of our international students toward the Faculty of Science. Why did they choose to study here? For more information, please contact us.
Hat Yai is considered to be the land of cultural melting pot of southern Thailand. You will find varieties of different ethnicities such as Buddhist Thais, Muslim Thai, and Chinese Thai. Apart from that, languages used in Hat Yai are Standard Thai, Southern Thai, Bahasa Melayu, and different Chinese dialects. As a result, the city becomes a diverse and open-minded place to spend life at. Finding a place to stay won't be difficult for you because the university provides on-campus dormitories for both PSU students and international students. However, the dormitories will be separated for male and female students. Besides, if you think staying outside is more challenging, off-campus accommodations can easily be found around the university. There are many styles of residences such as condominium, apartment, rented house, dorms, and others. For more information on the accommodations, please refer to the following QR code. Hat Yai is well known for its good food. A varieties of Thai, Chinese, and Muslim food are available. Here are some recommended foods that you should try while staying in Hat Yai. Considering the cost of living, you no need to pay a lot of expenses while staying here. Below is an estimated living expense for 1 year of study at PSU. However, it may differ depending on your lifestyle and general economy. You might be surprised at why the expense is not much expensive. The key reason is that the university has provided you with a wide range of facilities and infrastructure, cafeterias and food courts, the university central library, sporting facility, prayer rooms for Muslims, bank facilities, medical facilities, the university post office, convenience stores and bookshops, transports, security. Apart from the facilities and infrastructure, the university has also provided you with some free services. PSU Computer Centers offer services including computer repair service for all students and staff. To extend the visa, the International Relations Office at the faculty will help you in all processes. For graduate and international students, you are not required to wear faculty uniform. However, make sure to wear appropriate clothing when attending your classes. Shoulders and knees covered for both sexes. Hat Yai and Songkhla offer you many choices for trips and sightseeing, both natural and cultural places. Following are the most famous places to visit. For more information, please contact us.
I hope you enjoyed the video. If you are interested to come here either as a graduate student or to pursue your research career, please feel free to contact us. You are very welcome, and I guarantee that you will fall in love with this city, Hat Yai, Thailand. So the next session is very special. This year, we have Professor Takaaki Kajita, who was awarded the 2015 Nobel Prize in Physics for discovering the oscillations of neutrinos from one flavor to another, which proves that those subatomic particles have mass. So let me introduce the keynote speaker. Professor Takaaki Kajita is the Special University Professor at the University of Tokyo and also the Director of the Institute for Cosmic Ray Research of the University of Tokyo. Professor Kajita received his PhD from the University of Tokyo School of Science in 1986 and has been researching at Kamiokande and Super Kamiokande detectors at the Kamioka Observatory in central Japan. In 1998, at the Neutrino International Conference held in Takayama, Chifu, he showed the analysis results which provided strong evidence for atmospheric neutrino oscillations. In 2015, he shared the Nobel Prize in Physics for his role in discovering atmospheric neutrino oscillations. Currently, he also is the project leader of GAGRA. Now we are very excited and honored to hear his talk entitled Exploring the Universe with Neutrinos and Gravitational Waves. Everyone, please welcome Professor Takaaki Kajita.
Thank you. Thank you very much. Good morning. It's my pleasure and honor to give a talk in your meeting. Now, let me share my slides. Okay, I hope you can see. Okay, so let's begin. So today, I'm going to talk about the universe, exploring the universe with neutrinos and gravitational waves. Okay, this is the outline. First, I have a brief introduction on essentially on cosmic rays. Then I'm going to talk about neutrinos. And in particular, I'm going to talk about the experiments, Kamiokande, Super Kamiokande, and Hyper Kamiokande. Then I want to move on to the gravitational waves, and I want to discuss the KAGRA project, and I'll summarize this talk. Okay, now, Victor Hess measured the intensity of radiation at the balloon altitude. Then he discovered that the intensity increased with altitude. This means these radiations are coming from the space. Therefore, this was the discovery of cosmic radiation. and in fact the discovery of cosmic rays. So through this observation, we learned that there are phenomena in the universe that cannot be observed with optical telescopes. Also, we had a question: how, where, and how these particles are accelerated in the universe. So, since this discovery, we have been studying cosmic rays in order to understand the violent non-thermal phenomena in the universe. And well, in our university, University of Tokyo, Cosmic Ray Observatory was established in 1953 to observe cosmic rays. Then, Cosmic Ray Observatory was reorganized to Institute for Cosmic Ray Research of the University of Tokyo in 1976. This institute is called ICRR in short. And well, I belong to this institute, and I'd like to briefly introduce my institute. Our institute carries out various studies on cosmic rays, and here I show the map of our facilities. For example, in the United States, we have a telescope array experiment, and this is the experiment to study the highest energy cosmic rays. And in La Palma, Spain, we have the CTA North facility and the MAGIC telescopes. These are the facilities to observe the high energy gamma rays from the universe. And in Tibet, we have the air shower array called Tibet AS Gamma experiment. This is the experiment to study the galactic cosmic rays and very high energy gamma rays. And we have a plan to extend the study of the galactic cosmic rays at the Northern Hemisphere. And this is called Alpaca project, to be installed in Jakarta, in Bolivia. Furthermore, in Japan, we have the Super Kamiokande facility here. Also, we have the Kagura facility here. Super Kamiokande is for neutrino studies, and Kagura is for the gravitational wave studies. And today, I'm going to talk about the neutrino and gravitational wave studies in our institute. Okay, now I want to discuss neutrinos. Well, this is just an introduction about the neutrinos. Neutrinos are fundamental particles like electrons and quarks. Neutrinos are something like electrons without electric charge. And in fact, this feature has a significant impact. Neutrinos can easily pass through the Earth or even the Sun. Therefore, neutrinos can bring information of the fundamental processes at the center of the stars. So therefore, neutrinos are very important particles to study the universe. And here in the lower part of this slide, I show how we observe these neutrinos. Neutrinos essentially pass through everything, but sometimes interact with the nucleus. Then, in this case, typically charged particle is emitted, then this particle, if they propagate in the water, emit photons. These photons are called Cherenkov photons, and therefore we observe these photons by photodetectors. So this way, we observe neutrino interactions. Okay, now I'd like to move on to our experiments, Kamiokande, Super Kamiokande, and Hyper Kamiokande. But let me begin the experiments in the 80s. In the 1980s, large underground detectors were constructed to observe proton decays. Was the Kamiokande experiment. It had 3,000-ton detector volume, detector mass, and located in Japan. Another example was the IMB experiment. It had larger mass, 8,000 tons, and this was located in the United States. These detectors, unfortunately, did not observe proton decays, but these detectors played very important roles in neutrino astronomy, as discussed in the next pages. Well, in February 1987, a supernova was observed at the Large Magellanic Cloud, which was about 160 light years away from the Earth. And here I show the photos just before and after the supernova explosion. And you can see a very bright star after the explosion. And at that time, both the Kamiokande and IMB experiments were taking data. And these experiments, together with the Russian Baksan experiment, observed neutrino bursts. And in total, these three experiments observed 24 neutrino events. And here I show these 24 events as a function, and the vertical axis is the event energy. So you can see within about 10 seconds, neutrino events whose energies are between, say, 7-8 MeV to 40-50 MeV were observed. Well, there were only 24 events, but these 24 events were good enough to understand the basic mechanism of the supernova explosion. That means we understood that a heavy star, when it finishes its life, they can no more produce energy by nuclear fusion processes. Therefore, at the end of the life, they collapse. And the proto-neutron stars are created at the center of the star. And from there, neutrinos are emitted. And at the same time, outside of the star is exploded. So with this observation, we understood the basic mechanism of the supernova explosion. and therefore Professor Koshiba received Nobel Prize in Physics in 2002. Now, since Kamio Kande played a very important role in neutrino astronomy, the Japanese government approved the next generation experiment, that is the Super Kamio Kande experiment. Here, I showed a photo of the Super Kamio Kande detector. This photo was taken in 1996, when we essentially finished the construction of the detector. Well, Super Kamio Kande was constructed to study neutrinos, and in fact, Super Kamio Kande contributed to the discoveries of neutrino oscillations, which opened the window to study the physics beyond the standard model of particle physics. I show the discovery of atomic neutrino oscillations. Here, in this left panel, the horizontal axis is the zenith angle, and the vertical axis is the number of events. And you can see for downgoing neutrinos, the observed and the expected number of events were in good agreement. However, for the upward-going neutrinos, we observed almost a factor of 2 deficit compared with the expectation. And this was naively explained if we include neutrino oscillations. And in fact, the world community was convinced that this is the evidence for neutrino oscillations. Also, Super Kamio Kande and the Canadian snow experiment discovered the solar neutrino oscillations. Here in this plot, I showed the constraints from various measurements on the nu E flux, which is shown in the horizontal axis, and the nu mu plus nu tau flux, which is shown in the vertical axis. And this black band is the constraint from Super Kamio Kande. And the green, red, and blue bands are constraints from snow. And you can see these 4 constraints have an overlapping region here, and which suggests non-zero nu mu plus nu tau flux. Therefore, this is the evidence for solar neutrino oscillations. And by the way, I think I should say the main player for the discovery of the solar neutrino oscillation was the snow experiment. But as indicated here, Super Kamio Kande also contributed to this discovery. Anyway, Super Kamio Kande contributed substantially to the discovery of neutrino oscillations. But, of course, we wanted to contribute to the neutrino astronomy. And since 1996, we have been searching for the supernova explosion, neutrino burst. Unfortunately, in Super Kamio Kande, we have never observed neutrino burst. But we think supernova explosion is so important to understand the mechanism of the explosion or the history of the universe. In fact, well, this is the cartoon of the universe, and during this universe, there have been many supernova explosions. And during these supernova explosions, neutrinos were created, and these neutrinos should be traveling in the present-day universe, and therefore some of these neutrinos must be coming to the Super Kamiokande detector. Therefore, Super Kamiokande collaboration would like to observe neutrinos produced by the supernova explosions in the past universe. Well, okay, this is a very important motivation. However, unfortunately, the original Super Kamiokande was not powerful enough to observe these past supernova neutrinos. And therefore, we wanted to improve the performance of the Super Kamiokande detector. Well, in the supernova explosion, many new EBAs are produced, and these new EBAs interact with a proton, producing a positron and a neutron. Of course, we observe the positron signal, but so far, we were unable to observe the neutron signal. However, if we put gadolinium into the Super Kamiokande water, then these neutrons can be captured by gadolinium. Then this gadolinium emits gamma rays with the total energy of about 8 MeV. And these gamma rays are converted to the electrons, and therefore these electrons emit Cherenkov photons. And therefore, this way, we can observe the neutrons. And therefore, if we observe both E plus signal and the neutron signal, we have the high confidence that we observe the anti-electron neutrinos. And this way, we can reduce the background events. So we wanted to put gadolinium into the Super Kamiokande water. And the question is, how much gadolinium shall we put into the Super Kamiokande tank? Well, here I show the gadolinium sulfate concentration and the neutron capture efficiency. And the gadolinium sulfate concentration is 0.02%. Then the neutron, essentially 50% of the neutrons are captured by gadolinium, or if the concentration is 0.2%, then 90% of the gadoliniums will be captured. So we decided to put gadolinium with the concentration of 0.02% at the beginning, and eventually as high as possible, maybe possibly 0.2%. And this is the expected signal and background in Super Kamiokande gadolinium phase. If we observe 10 years, then these red, black, and green histograms are the expected signal, and these are the total background expectation. So, depending on the model, Super Kamiokande should be able to observe the past supernova neutrinos with the statistical significance between 2 sigma and 4-point-some sigma. Okay, so we decided to put gadolinium into the Super Kamiokande tank. Unfortunately, to tell the truth, Super Kamiokande had some water leak until 2018. But if there is a water leak, we are unable to put gadolinium into the tank. Therefore, we decided to repair the Super Kamiokande tank And this repairment work was carried out in 2018. So in the left photo, I show our repairment work. And in the right side, I show the Super Kamiokande tank. Anyway, this repairment work was very successful, and the Super Kamiokande has started the search for past supernova neutrinos with gadolinium-loaded water in 2020. So we want to get some interesting result in 5 to 10 years. Now, so far I discussed the Super Kamiokande experiment. And I would say that Kamiokande and Super Kamiokande have been very, very successful. Therefore, I think it is natural to think about the future water Cherenkov detector. And in fact, the future experiment is called Hyper-Kamiokande. Here, I want to briefly discuss the Hyper-Kamiokande experiment. The total and fiducial volumes are 0.26 and 0.19 megatons respectively. And in fact, the Hyper-Kamiokande will be about 72 meters in height and 68 meters in diameter. So it's going to be really a huge detector. And this experiment will have many important research topics in neutrino physics and astrophysics. The construction of this detector started in 2020, and it is an international collaboration. We have about 450 collaborators from 19 countries. And the experiment is expected to start in 2027. And since there are many important topics, but let me just mention one example. I showed that in 1987, 3 experiments observed a neutrino burst. The total number of events from these 3 experiments was only 24 events. Now, let's assume the next supernova explosion at the center of our galaxy. Then we expect to observe about 50,000 to 100,000 events in the Hyper-Kamiokande detector. And for example, in the left figure, I plotted the number of events as a function of time after the explosion. So, after the core collapse. So clearly, the time profile depends very much on the details of the model, and therefore we expect that we can understand the details of the mechanism of the supernova explosion by observing the neutrino burst of a supernova explosion. Okay, now I want to move on to the gravitational waves. Well, gravitational waves were predicted slightly more than 100 years ago in 1916 based on Einstein's theory of general relativity. And here I'd like to show you a movie, how the gravitational waves are generated. Here you can see 2 small black dots. They are 2 black holes. So this is a binary black hole system. Therefore, these 2 black holes are orbiting each other. And from this system, the gravitational waves are emitted. So I just want to show you the movie. So, oh, sorry. So you can see two black holes. By the way, the colors indicate the distortion of the space-time. And in the lower panel, you can see the emission, how the gravitational waves are emitted. With the emission of the gravitational waves, two black holes come closer and orbit faster. And since it's a movie, it slows down. And here, two black holes merged. A new heavier black hole is formed. And if you look at the outer space, you can see the gravitational waves are propagating to the outer space. So this is the image of the gravitational wave. In fact, slightly more than 5 years ago, on September 14th, 2015, LIGO observed the signals in their two laser interferometers. They are shown here. And clearly, these two data shown by red and blue curves, they agreed quite well. And therefore, LIGO concluded this cannot be the background. And the data told us that two black holes of 36 solar mass and 29 solar mass each merged at a distance of 1.3 billion light years, newly forming a 62 solar mass black hole. By the way, 36 plus 29 is 65, but the produced black hole's mass is 62 solar mass. So during this merger, 3 solar mass was converted to the energy of the gravitational wave. So in a sense, this was the most energetic event we ever observed. By the way, these signals were observed by the very large laser interferometer located in these two locations in United States. Well, that was slightly more than 5 years ago. Now, this is the more updated events. LIGO and European Virgo observed many black hole mergers. And here, the vertical axis is the mass of stars. And typically, LIGO and Virgo observed black hole mergers with the mass of, say, more than 10 times the solar mass. And sometimes this mass is very high, nearly 100 solar mass. So these black holes are rather heavy, and therefore people are now wondering how were these heavy black holes created. In addition, you can see these two events. These are the mergers of the neutron stars. In fact, the first event observed was identified by optical telescopes. And these optical telescopes had a very detailed follow-up observations. And through these, people realized that the neutron star mergers are the sources of the heavy metals such as gold or platinum. Okay, well, here I'd like to summarize the science with ground-based gravitational wave detectors. Well, first I discussed the merger of binary black holes, and I discussed that the mass of these black holes were rather heavy. Therefore, the new question is how the black holes are formed or created. The second target is the merger of the binary neutron stars, and through the observations of these mergers, we'd like to understand the origin of the heavy metals in the universe. Also, we would like to understand what is the inside of the neutron stars, or how large is the neutron star. And finally, we'd like to observe supernova explosion. And of course, we'd like to understand how the heavy stars finish their life. Okay, so it's clear that with the gravitational waves, we can understand many important questions in the universe. Therefore, we have been constructing the Kagura interferometer. It is an international collaboration, mostly from the Asian countries. Kagura, well, here I show the map of the experiment. Well, in this mountain, there is Super Kamiokande. Now, in the same mountain, we have the Kagura laser interferometer. We have installed the 3 kilometer by 3 kilometer laser interferometer in underground, because in underground, the seismic noises are very small. Well, seismic noises are approximately 2 orders of magnitude smaller compared with the surface. In addition, we have to reduce, excuse me, we have to reduce the various noises in the laser interferometer. One of the noises are the thermal noise of the mirrors. Therefore, we decided to cool down the mirrors to the cryogenic temperatures. Anyway, the Kagura project was approved in 2010, and we started the excavation of the tunnel. After finishing the excavation, we installed the vacuum tubes to the 3 kilometer by 3 kilometer arms. And here I show you both arms. And the connection and the leak test of the 3 kilometer by 3 kilometer beam tubes have been finished in March 2015. Then we began the installation of the mirrors. And this is a very important mirror. This is one of the 4 main mirrors of the Kagura interferometer. This mirror is going to be cooled down to 20 Kelvin. And this is a sapphire mirror whose diameter is 22 centimeters and the thickness is 15 centimeters. The weight is 23 kilograms. By the way, you can see some red color here at the surface of the mirror. This is the protection of the surface. Since this mirror is exposed to the very intense laser beam, if we have one small particle attached to the surface of the mirror, we have a problem. Therefore, the surface is protected by this coating. After the installation of the mirror into the vacuum tank, we remove this coating. And in the right side, I show you the installation of the first cryogenic mirror. That was this photo was taken in November 30th, 2017. After that, all the mirrors were installed. And this is the more updated photo of the Kagura interferometer. This is the center of the laser interferometer. And in fact, at the center of the vacuum tank here, there is a beam splitter. So the beam is divided into two. One goes to this way, another goes to this way. Oh, sorry, this way. Okay. Anyway, this photo was taken in spring 2020. After the completion of the construction of the laser interferometer, we have to, of course, operate the interferometer. But the operation of the interferometer is carried out completely automatically outside of the tunnel, because if there is a human activity inside the tunnel for the operation of the laser interferometer, that will be a noise source. Therefore, everything related to the operation is carried out at the outside building. Anyway, I'd like to show you the Kagura sensitivity history. Kagura has finished the installation in the spring of 2019. Then in August 2019, we had the first successful laser interferometer operation. And at that time, the sensitivity was this, is shown here by the green curve. Since that time, we continuously try to improve the sensitivity. And we started the observation in the spring of 2020. And at that time, the sensitivity is shown by this red curve. And you can see, for example, around 300 Hertz, we have improved the sensitivity by 4 orders of magnitude. And this is the design sensitivity around 300 Hertz. We were by approximately factor of 30 to the design sensitivity. Anyway, we started the observation in the spring of 2020. But unfortunately, due to COVID-19, no one was able to come to the site. Therefore, at the site, there were very limited number of people. Therefore, we were unable to continue the operation. So we stopped the operation in 2 weeks. Okay, now, well, certainly, even at this moment, Kagura is stopping the the operation. So from now on, I'd like to discuss the future of the Kagura and gravitational waves. First of all, scientific output will be maximized by the global network. Even if a very clean signal is observed in a single detector, we cannot get any information about the direction of the arrival direction of the gravitational wave. If we have no arrival direction information, then we are essentially unable to explore the universe with the follow-up observations by optical telescopes. So clearly, we have, on the other hand, if we have the network observation by the global gravitational wave detectors, then by observing the signal arrival time, we can estimate the signal arrival direction. So clearly, the global network is very important. Therefore, Kagura is going to join the global network. And we'd like to start the observation in 2022. And this is the timeline of the global gravitational wave observations. And well, until now, LIGO and Virgo had 3 observations. Observation 1, observation 2, and observation 3. The next one is observation 4 or 04. Unfortunately, due to COVID-19, the preparation work had to slow down. Therefore, at this moment, we decided that we will not start the next observation before June 2022. Well, 2 pages ago, I mentioned the importance of the global network. And here, I would like to show you the importance of Kagura. If we have LIGO interferometers in United States and Virgo in Europe only, then the sky localization of the signals are like this. So clearly, for some arrival directions, even if there's only LIGO and Virgo, they can observe the signal arrival direction rather clearly. But for some other directions, the determination of the signal arrival direction is rather poor. But if we have the Kagura interferometer, then essentially for any direction, we can precisely determine the signal arrival direction. So clearly, Kagura is very important for the global gravitational wave network. Well, so far, I discussed the neutrino studies and gravitational wave studies separately. However, I think neutrinos and gravitational waves should work together. Because, for example, if a supernova explodes at the center of the Milky Way galaxy, then we expect to observe both gravitational wave signals and neutrino signals. And by combining these 2 signals, we can truly understand the mechanism of the supernova explosion. So, gravitational waves and neutrinos should work together. Okay, let me summarize. We are in the era of the multi-messenger astronomy. Neutrinos and gravitational waves play very important roles. The interior of the stars can be studied with neutrinos. Experiments in Kamioka have been contributed to the neutrino astronomy. The next generation detector, Hyper-Kamiokande, will contribute further to the neutrino astronomy. Gravitational wave astronomy was born about 5 years ago. The early results from LIGO and Virgo have been extremely exciting. And Kagura is the first large-scale laser interferometer with cryogenic mirrors and a deep underground site. And we'd like to begin the operation of Kagura in 2022 and contribute to the gravitational wave astronomy. Okay, that's all from me.
Much, Professor Kajita, for the excellent and inspiration talk. Now it's time for the questions and answers. If any of the audience have any questions, you can type your question on the Facebook Live, on the Facebook Live on Facebook page, Faculty of Science, Prince of Songkhla University. I have a few questions in my hands right now. So let's go to the first question from Professor David Lafaro, Mahidol University, Bangkok. Professor David asking that, Professor Kajita, could you kindly tell us your perspective about a report this month that in November 2020, there was a 300 tera electron volt gamma ray flare from the Cygnus cocoon in our galaxy, and also an ice cube neutrino event from that region within the time period.
Oh, I see. That's quite exciting. Well, I'm very sorry. I don't know the details of this very important event, but clearly this is really exciting.
So the next question is from Dr. Narakorn from PSU. He asking that why nature flavors the neutrinos oscillation mechanism than the non-transform one.
So the question is why neutrinos can change their flavor, right? Yeah, okay. But there are three neutrino types: electron neutrinos, muon neutrinos, and tau neutrinos. And well, because there are three types, there should be three mass eigenstates. And well, okay, three flavor eigenstates and three mass eigenstates cannot be, well, do not need to be identical. Therefore, for example, electron neutrinos are the mixture of these three mass eigenstates. And therefore, for example, if an electron neutrino begin to propagate, then three mass eigenstates propagate coherently. But since the mass is different, therefore, after some time, the phase of the three mass eigenstates cannot be identical with the initial state. This means after some propagation, the electron neutrinos cannot be the original electron neutrino, should be some mixture of electron neutrinos plus some other flavor states. So this is essentially the mechanism of the neutrino oscillations.
Thank you very much. And the next question is quite general, but might be useful for the young students and the scientists today. Can you recommend to us what it takes to be as successful as you? If the young students want to be a Nobel laureate in the future, what they have to do?
Oh, thank you for this question. Well, I'm sorry, I don't have a very good answer. I cannot guarantee the way to get the Nobel Prize, but let me mention, well, certainly I was involved in Kamiokande when I was a graduate course student, and I was really excited with the experiment. I thought that this experiment will be very important, and therefore I was really deeply involved in the Kamiokande experiment. And well, to be honest, I was extremely lucky. And after getting my PhD, I tried to improve the analysis in Kamiokande. And during the improvement work, I found that the neutrino data observed in Kamiokande was a bit strange. And I I thought I should work why the data looks strange. So I worked on the neutrino data very intensively. Well, in fact, I worked on neutrinos for more than 10 years. And because of this very intense work, finally I was able to observe neutrino oscillations. So therefore, the only suggestion I can tell you is you should be interested in your research and you should work hard.
Very important, right? And you have to love what you do too to get to that point. So the next question is from Dr. Patipan Uttayarat. The question is the Hyper K going to replace the existing Super K tank, or is it will be a new separate tank?
Yeah, thank you. Yes, the hyperkamiokande tank will be a new separate tank. In fact, in the superkamiokande in the mountain where the superkamiokande is located, there's no more candidate space for the hyperkamiokande tank. Therefore, the hyperkamiokande will be located in a nearby but separate mountain.
And the next question is from a PSU student, Apisit Dang Iet. He's asking that why do we need to observe neutrino in the underground? Why don't we do it on the normal ground?
Oh, I see. In underground. Yeah, well, as I mentioned, neutrino interactions are very rare. On the other hand, we have many backgrounds. Even in 1,000 meter underground, we have cosmic ray background events. But 1,000 meter deep underground is very important to reduce the cosmic ray background. Compared with the surface, our cosmic ray background rate is reduced by 5 orders of magnitude. So with this background reduction, we are able to observe the clean neutrino signals.
There is another question. Would Jiangmen Underground Neutrino Observatory enhance neutrino research? Jiangmen Underground Neutrino Observatory, would it enhance the neutrino research too? I don't quite understand the question too, actually. maybe we skip this question. I think there's no more question already, so let me summarize this talk. So I would like to thank Professor Kajita for the excellent talk, and it has been very, very lucky and honor for us to have you here today at our small conference. So thank you so much for your time today, and hope that we will have the opportunity to see you sometime in the future in person. Thank you very much. Arigatou gozaimasu.
Thank you very much. Bye-bye.
So now we come to the end of our live broadcasting opening ceremony. Before we end the session, I would like to inform you that after the opening ceremony, the oral sessions will be carried out via 3 simultaneous Zoom rooms. Please kindly enter the room that you wish to participate in. You can find the link to each room in the email. But if you cannot find your email, please try to look at your spam folder or on the SPC website. Also, the abstract book is now on SPC website already. So now on behalf of the organizing committees, I would like to thank all of you for joining us today and wish you to have a great day. Be safe and stay healthy. Thank you very much and see you in the Zoom meeting room. ขอบคุณค่ะ Thank you very much ค่ะ Professor Kajita.
Over half a century ago, Prince of Songkla University, or PSU, has been established as the first source of higher education in southern Thailand. Today, although there are hundreds of universities throughout Thailand, PSU is still one of the country's leading institutions of higher education. We use our research-based knowledge and experiences accumulated through the last 50 years to create practical innovations to improve the quality of life in our southern communities. With a broad vision, we pioneered several programs. With the continuous aim to make progress for Thai economics and society on the global stage. Having started with only 2 campuses and 3 faculties, we have at present 5 campuses situated at key locations of the southern region, covering every field of knowledge by 37 faculties, research centers, and various other academic agencies. We provide knowledge to students in 320 academic fields, corresponding to the needs of the region, country, and the global community. Our consistently high educational quality is maintained by continuously improving our educational programs to be up to date with the latest advances of international academia. Our learning resources not only provide academic content, but also enlighten students in terms of both mindset and experiences. While education quality is ensured by our highly qualified academics. Experienced instructors and professional educators of global renown. Our 5 campuses offer safe academic environments in peaceful, natural surroundings, containing a cohesive academic community that cultivates integrity and a keen sense of social awareness. We are united in embracing diversity, which serves as a foundation to our peaceful, multicultural society. Our educational programs have been developed together with accordance with research, utilizing resources, culture, wisdom, and economics surrounding our 5 campuses on the Thai Peninsula. This enabled us to become a leader in various types of academic fields, particularly those relevant to the fundamental potential of the South. Our constant determination to enhance the university's competence and mobilize Thai society resulted in PSU becoming a research university with new sources of knowledge. We apply our experiences, expertise, and resources to respond to the most pressing social and environmental issues of our time. We also learn how to apply traditional wisdom to preserve and maintain our cultural heritage. We create new economic opportunities based on the productivity profile of the region. We create mechanisms of propagating practical knowledge to entrepreneurs. We introduce modern innovations to assist in the creation of new alternative industries and services. We offer improved medical and public health services while constantly pushing the boundaries of medical science knowledge in order to develop our country to be the center of healthcare in ASEAN. We communicate our expertise to the outside world through several networks and means in order to disseminate knowledge, share ideas, and foster a lifelong learning behavior among people of all ages and occupations. PSU is more than just a university. We provide education to all levels, from preschool to PhD. In addition to benefiting all social sectors, PSU also produces alumni widely successful in various professions. Besides teaching in classrooms, our instructors also reach out to communities and propagate practical knowledge to people of all ages and educational levels. In addition to working in laboratories, our researchers also work on palm plantations, rubber plants, fishing boats, in the mountains, under the sea, and in remote forest villages. Besides working on campus, our staff kindly helps people in need outside the university as well. The PSU community closely follows the resolution of His Royal Highness Prince Mahidol Adulyadej, the Prince Father. Let consideration of personal gain take second place to the overall benefits of mankind, good fortune, wealth, and prestige, and come naturally to those who are spiritually dedicated to their work. This resolution has been the guiding foundation of PSU people's ideating to find new sustainable methods to advance our society for the benefit of mankind.